All right, so far we've talked about um, different types of nuclear decay, different types of nuclear reactions. And now we'll start to look at sort of the kinetics of those processes. So when we're looking at radioactive decay, so taking that unstable nucleus and having it break down into some other element, whether it's alpha decay, beta decay, positron emission, whatever it may be, we're going to see that it undergoes a first order process, or it follows first order kinetics, I should say. So if we think back to chapter, I want to say 14, where we were actually looking at chemical kinetics, we were looking at the different orders of reactions, and we saw we had different integrated rate laws. We saw for a first order process, we could kind of get rid of that piece. Oops. We could kind of get rid of the piece on the bottom, and then we'd have plus the natural log of NO, so that initial amount. So when we're looking at the equation I have here, as it is, this is saying the natural log of the amount of that radioactive material at time t is going to be equal to the negative rate constant times the amount of time that's passed plus the natural log of the initial amount. So the equation that's on the slide originally here is just a rearrangement of that one. So we subtracted the natural log of that original amount from both sides. And then with the properties of logs, we could combine that just into a single fraction. So rather than have natural log of NT minus natural log of NO, we were able to just combine both of those into a single fraction, or a single term. And with it, if we now think about the half-life, so the amount of time it takes for 50% of that substance to decay, we could essentially take the NT here, and instead of NT, we could have 1/2 NO. Let's just get rid of that for a second. So if we substituted that in for the half-life, because this is going to be 50% of whatever this is, we'll see that the initial amounts there, NO, is going to cancel on the top and the bottom. So we'll just be left with natural log of 1/2, which is going to be 0.693, negative 0.693. So if we divide by negative K, we can then get the half-life of this process is going to be equal to 0.693 minus whatever that rate constant is going to be. And again, that'll be different for each radioactive nuclei. They'll decay at different rates, so they're going to have different half-lives as well. But what this allows us to do is figure out how long, if we, for a particular radioactive isotope, how long is it going to take for 50% of that substance to decay? Or if we think back to the previous equation from the last slide, if we know the rate constant, or we know how much of the substance we have, and we know how much of the substance we have initially, we can figure out after a certain amount of time has passed how much of that radioactive substance is still going to remain. Or if we have 3 of the 4 variables, because we'll have the initial amount, we'll have the amount at whatever time we're interested in, we'll have time itself, and then that rate constant. As long as we have 3 of those 4 variables, we'll be able to solve for the 4th one. So looking at the question here, there's going to be actually 2 different ways we can solve this one. We'll have the equation, which is going to work for every type of question like this one. And then in particular with, or for this particular question, there's going to be another way we could approach it. But that'll only work with certain questions where the values were given sort of work out nicely. But with the question we have here, the half-life of cobalt-60 is 5.27 years. How much of a 1 milligram sample of cobalt is left after 15.81 years? So in this case, we have, if we think about the equation, we have the initial amount. We're trying to figure out the amount at time t. We have time itself, 15.81 years, but we're missing that rate constant. So in terms of the steps we need to follow for this question, we need to figure out, based on that half-life, what is the rate constant, what is K? And then once we have that K value, then we can plug it into our first order integrated rate law in order to solve for the concentration at that time. So for the first step, oops. I don't know why it showed up like that. But the first step here, we've got the half-life equation. In this case, we know what the half-life is. So if we cross multiply and then just divide by 5.27, ultimately we'll have K is equal to 0.693 over 5.27 years. So that's going to give us a value of 0.131. And then because the half-life itself is in years, that's going to mean the unit on this rate constant is going to be inverse years. But now with the equation at the bottom, that's our integrated rate law. And in this case, I expanded it because we're solving for the amount at this time. So with the radioactive decay questions like this, we're not going to be solving for a concentration. It's just going to be an amount. So in this case, milligrams. But it's still going to work the same as with the concentration from the first order rate laws in chapter 14. But in this case, I just rearranged the equation because we had natural log of NT over NO. So I expanded that out into the subtraction using the properties of logs, and then just added natural log of that initial amount to both sides so that we had this term on the left by itself. And then with the rest of this equation, K, we just solved for. T, we were given in the question. And then the natural log of that initial amount, we started with 1 milligram. So just plugging all of that in, we're going to wind up with a value at this time of 0.125 milligrams. And like I said, this equation is going to work for every single type of question like this. Depending on what it is, we may have to solve for a different variable. In some cases, we may already have K and we don't have to go through this step up here. So the steps themselves are going to be different, or may be different, I should say. But the equation itself is going to be something we can always use for this one. But with this particular question, we could also approach it in a different way. And the reason it's going to work for this one is because the amount of time that's passed is a multiple of the half-life itself, so 15.81 years. If we divide that by the half-life, 5.27 years, we're going to get 3 exactly. And then if we think about what a half-life represents, 50% of that remaining material is going to decay. So if we had 3 half-lives here, 3 half-lives are going to pass. That means we'll go from 100% of that substance. And then after the first half-life, we'll be down to 50%. After the second half-life, we would be down to 25%. And then after that third half-life now, again, we're going to cut it in half one more time, we're going to be down to 12.5%. And then if you think about it, 12.5 of 1 milligram is just going to be the 0.125 milligrams we saw for initially. But again, this is only going to work in the case that we have an exact multiple of the number of half-lives. So if we had 16 years instead, 5.27 isn't going to go evenly into that. So we would have to go through the equation one for sure. But in the case where we have an exact number of half-lives, an integer value of half-lives, in that case, we could see how many half-lives are going to pass and then just divide that initial value in half that many times. So again, in this case, I divided it in half 3 times. I didn't divide by 3 though. That's going to be a completely different value, which just won't work. Okay. And then with this process, we can also use it for radiocarbon dating. So with the question here, would an object from an archaeological site is subjected to radiocarbon dating? The activity of the sample that is due to carbon-14 is measured to be 11.6 disintegrations per second. The activity of a carbon sample of equal mass from fresh wood is 15.2 disintegrations per second. The half-life of carbon-14 is 5,715 years. What is the age of the archaeological sample, excuse me. So with this one, if we again think about what the half-life represents, We can make a little graph here and hopefully this comes out okay. But we'll have 100, whatever, 50, and I'll just do 25 to keep it easy. And then if we just think about like whatever this half-life is, 1, 2. After one half-life, we'll be down to 50. And then after 2 half-lives, we'll be down to 25. So in each case, we're losing 50% of what we already had. And the half-life itself is going to be the same length. But with each subsequent half-life, since we only had 50% of the previous one, the absolute quantity that's decaying is going to be less in each case. So again, if we think about this first half-life here, from 100% or 100, if you want to think about 100 grams of the sample, after the first half-life, we'll be down to 50. So we lost 50 grams. And then from the second one, this half-life length is going to be the same amount of time. So it could be 5,715 years. It could be whatever that half-life is going to be for that particular substance. But now in the second half-life here, we're only at 50 to start. So we're only going to lose 25 grams or 25 milligrams, whatever unit you want to use for this. So with each of these half-lives, we're seeing the amount of this substance or the rate at which it's decaying, the rate at which it's disintegrating. If you think about that unstable nuclei essentially just breaking down, is going to decrease. So what we can do in this case is look at the difference or look at the ratio in those two disintegration rates between the old sample, the archaeological sample, and the fresh one. And we can look to see what the difference is or what the ratio is there to get an idea of how long or how old that first sample is. And we can still use that integrated light rate law. So with this question again, 11.6 disintegrations per second for the archaeological sample, 15.2 for the fresh sample. So the first thing we need to do is figure out what K is. And we were given the half-life, 5,715 years. So if we just rearrange this equation, essentially just swap K and the half-life itself, we can get K, and it's going to have a value of 1.21 times 10 to the negative fourth inverse years. Again, it's inverse years because the half-life was given in years. If we had a half-life of 26 days, then the unit here for K would just be inverse days. So it's going to be dependent on what we're actually plugging in there for the units. But now that we have the half-life, or now that we have the rate constant, excuse me, we already had the half-life. Now that we have the rate constant, we're ultimately looking for time. What we're going to be able to do is use those disintegration rates to essentially represent how much of the sample we have. We'll be able to plug in 11.6 for the amount at time t. We'll plug in 15.2 for the amount at time 0. And then on the other side, negative kt. We just solve for k. T is what we're missing here. So we can just go through, make this just a regular number, 0.763, take the natural log of it. And then what we'll do is divide by negative k, just to get t by itself. And what we'll see in this case is we're going to have a time of 2,235 years. And then with these types of questions, we can always think about if that value makes sense in terms of the question we're given. Because the half-life for this one was 5,715 years, I think, something like that. So it's going to take that long for half of this substance to disappear, decay. We have more than half of it remaining, 11.6 compared to 15.2. So the amount of time should be less than this, because if it was equal to this or greater, we'd see even more of this substance would have decayed. So the fact that we get a value like 2,235 compared to the half-life of 5,715, that seems like a reasonable number, considering that we have about 76% of that substance remaining still. So we can always just double check, make sure we're on the right track there. If we wound up with something greater than this, We would want to go back, double check, make sure we included the negative sign, make sure we plugged in the pieces in the correct order, and just to have the correct algebraic steps, because we can at least make sure that the number seems reasonable for the question that we're asked. Okay, and now this one going to be a little bit more complicated, a little bit more going on with it. And we've got a couple questions that we need to answer. With the third piece here, with question C rather, let me get the drawing thing. Becquerel and Curie's, hopefully I'm pronouncing that right. I haven't heard anybody say it in a really long time. But these are just going to be units for activity. So how much radiation, or how fast is that substance, or how much of that substance is disintegrating, are going to be 2 units. And what we'll see is the Becquerel is going to be BQ, and 1 disintegration per second is going to be equal to the Becquerel. And then with the Curie, it's looking at the same thing. It's just a different unit for it, essentially. So if we think about kind of like meters and feet, both representing distance, we just have a different relationship there. And again, this one, dis per second, is disintegrations per second. So with the Becquerel and Curie, what we'll see is 37 billion rather. So 3.7 times 10 to the 10th. BQ will be equal to a single Curie. So the unit for Curie, or the symbol for Curie, is CI. And one of those Curies is going to be equal to 37 billion becquerels. But for this question, we start with 1 gram of strontium-90. 0.953 grams of this substance will remain after 2 years. We want to first figure out what the half-life of this isotope is. We want to figure out how much of this substance would remain after 5 years. And then finally, we want to determine the activity of this sample in becquerels and curies. So for the first two, we're going to be using the integrated rate law. For the first one, we'll have to figure out K, then we can use that to determine the half-life. And then for the second one, once we have K, we can figure out after 5 years what that remaining amount is going to be. And then with the third one, with C, we'll have to convert the units on K and then figure out how much of this strontium we actually have in order to get the actual units there. But with this strontium-90, I believe this is the substance. So when they were developing the atomic bomb during the Manhattan Project, part of the reason that they were developing, of course, was to fight the Nazis, who they had assumed was well ahead. So the Nazis actually started their atomic program a couple of years ahead of the Americans. So the Americans involved in Project Manhattan assumed that the Nazis were closer to actually completing that research of actually developing and having a usable nuclear weapon. Ultimately, the Germans never really got particularly close. Once the Nazi Party really started taking control of Germany, there was kind of an exodus of a lot of the intellectuals. So with the exception of Werner Heisenberg, there wasn't really anybody too brilliant remaining in that country anymore. So they never got particularly close. But as the Americans were developing the atomic bomb, Robert Oppenheimer, and I believe it was Enrico Fermi, might have been somebody else involved, but they were discussing different options as they were still working on the atomic bomb. And one of them was actually using strontium-90 to essentially poison the water and the food supply in Germany, as sort of a stopgap measure. I don't know how serious that conversation was, in terms of whether they would actually do it, whether it was feasible, whether it was possible. But that's just one story I'm familiar with related to this particular isotope. But now to see how we can actually work through this one. And again, if you want to pause it just like all of the previous ones, so you have a little bit of chance to work on your own, definitely feel free to do that one. Otherwise, I'm just going to kind of start going through A, B, and C here. And with the first one, like I said, if we want to get the half-life, we need to know what the rate constant is. So since we know the initial amount, we know the amount after time t, we know time, we can solve for k. So for part A here, we've got the natural log of the amount at time t over the initial amount is equal to negative k times time. So if we turn this into a number, natural log of this value is just some number, and divide it by -2 years, what we'll see is that rate constant is going to be 0.0241 inverse years. And again, inverse years because time is in years. If I had plugged in 760 days, or 730 days rather, to represent 2 years, we would still have the same rate constant. It's just going to be a different number, different units, inverse days. So it's important that we have the correct units there. And then once we have that k value, we can plug it into our half-life equation, 0.693 divided by k. And in this case, since we're having inverse years, now the half-life again is going to be represented in years. So it's going to have a half-life of just under 29 years. But with the second one, how much strontium-90 will remain after 5 years? Again, we have the rate constant now. So if we're thinking about this equation, the only piece we're missing is the amount after time t. But when we solve for b, what we're going to do is break this natural log into the two terms so that we can move the natural log of the initial concentration to the right-hand side. So in this case, we'll have natural log of whatever the amount is at that time is equal to -k, still that same rate constant. In this case, though, time is going to be 5 years, and it really should have 0.00 to represent the 3 significant figures there. But then plus the natural log of that original amount, that 1 gram. And we'll see this entire right-hand side, when we take the natural log and add it to the product of these two terms, is going to give us a value of -0.121. But that's equal to the natural log of this amount after time t. So in order to get rid of that natural log, we'll use the power, or we'll use e, essentially, e to the natural log of x, e to the -0.121, gets rid of that natural log, and we get a value of 0.886 grams. And those two are pretty similar to what we've seen for the previous example as well. But now with part C, it's going to be a little bit more involved. So the first thing we're going to have to do is take this rate constant, because these activity units are in, if we break them down, are essentially disintegrations per second. But this rate constant's in inverse years. So the first thing we're going to have to do is convert this rate constant to inverse seconds. And then once we have that, we'll have to figure out how many atoms of this strontium we actually have. So with the first part here, I've got everything just on the slide, so we'll kind of go through it. The first equation here is just taking this rate constant, 0.0241 inverse years, and then using dimensional analysis. So with inverse years, it's really 0.0241 over years. So that's why I've got years on top to start, is equal to 365 days. But we want inverse seconds, so we've got to continue through. 1 day is equal to 24 hours. Again, day and day cancel, year and year are going to cancel. 24 hours then is the unit we have is hours now, inverse hours. So in order to get rid of that, we'll put hours on top. And then you could do 60 minutes and then have minute on top of the next step, 60 seconds. Or we can just kind of combine those into two. But we'll see this rate constant, 0.0241 inverse years, is equivalent to 7.64 times 10 to the -10th inverse seconds. But what we'll do with the unit here is change it to disintegrations per atom per second. And let me change that a little bit more just to show that it's per atom per second on the bottom. So not just per atoms. But with the rate constant, if you think back to the, again, chapter 14, I believe it was, where we had a couple of experiments in a table, we had different concentrations, we had different reaction rates, and then we could use those different experiments in order to solve for the exponents, solve for the order of those reactants. And then depending on if it was second order or first order, the unit on that rate constant would actually change slightly in order to give us a reaction rate in terms of molar per second. So with the unit here, what we're going to see is we're going to change it slightly from inverse seconds. So that's really just seconds on the bottom. But since we're looking at nuclear decay, that's going to be, we're going to change it to disintegrations per atom per second. It's still going to be that same value, just the units here are going to be disintegrations per atom per second. And then if we think about this unit now, we've got to ultimately get to disintegrations per second. That's what a becquerel is. So in order to get to disintegrations per second, we need to cancel out this atom unit. And in order to do that, we need to figure out exactly how many atoms of strontium-90 we possess. And that's what this second line is showing. So 1 gram of strontium-90, again, that represents the mass. So 90 grams is going to be equal to 1 mole. We stopped at this point after this first parenthesis, that would be how many moles of this substance we have. But again, we've got atoms on the bottom that we need to cancel. So we've got to go one step further. We've got to use Avogadro's number. 1 mole of anything is equal to 6.022 times 10 to the 23rd. And in this case, since we're looking at strontium-90, that's going to represent the number of atoms of strontium-90, ultimately giving us a value of 6.7 times 10 to the 21st atoms. And that makes sense because 6.02 times 10 to the 23rd is for a mole, which is 90 grams of the substance. We only have 1 gram, so we have approximately 1/100th. So it makes sense that we have 2 orders of magnitude less than Avogadro's number. So again, with these questions, you can always kind of think about each of the values you're obtaining. Do they make sense in the context of the question of the numbers that you're using to get there? But this is how many atoms we have now. And again, disintegration per atom per second, we need to get rid of that atom unit. So what we're going to be able to do in the third step down here is just multiply these together. And in this case, I have the unit in purple for that rate constant. So atoms are going to cancel. We'll just be left with disintegrations per second when we multiply those two together. So we'll get 5.12 times 10 to the 12th disintegrations per second. And then again, that unit, disintegrations per second, is just equal to the becquerel. So that gives us the first half of part C. Now for the second half, determining the activity in Curies, we have to go one step further. In this case, we just have to do a dimensional analysis. So this would just be a unit conversion that you're given. You don't have to memorize that it's 37 billion for every 1 Curie. But since we've got BQ on top, we need to have BQ on the bottom. Ultimately just leaves us with the Curie unit, CI. And we'll see in this case, the activity would be expressed as 1.4 times 10 to the second Curies, which is really just 140 Curies. And then with that activity, one way we can measure it, so essentially just how much radiation, how radioactive is that substance, is going to be with a Geiger counter. A more qualitative method, so not getting a specific value on that activity, but a qualitative method that is sometimes used. I would assume OSHA and different workplace agencies would have a better sort of system for it. But one way that if you expect to be exposed to radiation, want to see how much of it you are exposed to, is to essentially just keep a thing of film with you, because the radiation itself is going to influence the film. And then the more radiation, just the more of that color on the film is going to change. So you can use that as kind of a qualitative gauge of measuring radioactivity. But what you can also do is just use a Geiger counter. So this will work similar to a smoke detector. So a smoke detector has a americium 241, I believe, and that's going to be radioactive. So it's only a very small amount, and it's in a confined sort of area, but it's going to eject alpha particles, which are then going to ionize the air. And then when it gets ionized, it's got positive ions, it's got the negative electrons that are then going to flow to create a current. And then in the smoke detector, when the current, is sort of cut off. So when we have the smoke actually present there, it's thick enough to block those alpha particles that don't have much penetrating ability. So we no longer have that current being produced. Just signals to the smoke detector to start creating that noise, the beep or whatever it's going to be for that particular detector. We're going to see something similar here, where the Geiger counter, we've got this window that's going to allow the radiation through. And then within it, we've got argon gas, so an inert gas. But the radiation itself is going to be able to ionize that gas. Again, create positive ions, negative electrons. And then since we've got a cathode and an anode, we're again going to be able to create a current. So if you've ever seen any sort of media, TV show, movie, whatever it may be, that's dealing with radiation or radioactive fallout, if they're trying to measure how radioactive that substance is going to be, typically they're going to be using a Geiger counter. And that's going to be the device that's going to make that clicking noise if there's radiation present. But that's just going to be kind of the basis of how those work. Just measuring how much of that gas is being ionized from that radiation. So if we had more radiation, we'd have more of that ionization. We'll have a larger current pass through. Or if there's less radiation, we'll get less ionization and, of course, less of a current then. And then with the clicking noise itself, because like I said, the Geiger counters make a clicking noise. I'm not sure if that's from the amplifier or the counter. That's what I would assume it would be from. But there may be some other component in here that's responsible for that. But if you do ever see something on TV or in a movie with radiation, it's making that clicking noise, it's going to be a Geiger counter that they're using. And then with the rest of this chapter, we're going to kind of focus on nuclear fission, nuclear fusion, and how those relate to nuclear weapons, and nuclear energy, nuclear power, so power plants and things like that. But one other thing I want to mention is just the radioisotopes are used as radio tracers. So when I was doing graduate research, for instance, we would measure the concentration of pesticides on like plants at different points after they were sprayed, just to see how long they stick around for or how fast do they dissipate. And in order to do that, in order to make sure our analysis was accurate, we would use radioisotopes in the extraction process. So if we're thinking about a leaf, for instance, that has some pesticide on it, we can't simply just look at that leaf and know exactly how much of that pesticide is present. We've got to do a full sort of workup on it, which includes extracting the material that we're interested in, leaving behind as much of everything else as we can, and then ultimately there's several steps in it, ultimately leading to analysis, ultimately leading to quantification. But the extraction process itself isn't perfect, so you don't always get 100% of your sample. So what we would do is, before the extraction, take the leaf sample and then add a radioisotope to it that's going to be similar to the chemical of interest. Because with that radioisotope, it may just have carbon-14 or carbon-13. It may have deuterium instead of hydrogen-1, but it's just going to have some sort of radioactive isotope that's not going to be present in nature. So we can apply a specific amount of that substance and then sort of track it through the entire extraction process as sort of what's the word I'm looking for? A standard, in order to make sure that we're accounting for any of that analyte that we're actually interested in, any of that analyte that's going to be left behind. Because let's say during the extraction process, if we had, at the end of it, if we had 80% of the radioactive isotope in our analyzed sample, that means 20% of it was lost throughout the extraction process. So we can apply that ratio, we can apply that loss to the analyte itself. And again, we have to be selective about it. You have to pick a you have to pick a chemical that's going to be similar to your analyte. You can't just pick any random thing. But that's going to be one application of these radioisotopes, kind of a radio tracer. But the more common example is going to be medicinal practices. So they can administer these radioisotopes to patients, and then depending on the particular isotope, you can see a handful of different uses here. But they're going to work similar in the sense that they're then going to be able to be traced through the body. In some cases, like with iodine 123, it's going to collect in the thyroid. And then with that, we can then image the thyroid, get better understanding of how it's working or if it's not working. And like I said, the rest of these are going to be similar sort of concepts. But also notice with these different radioisotopes, the half-lives on them are going to be extremely small. So, and extremely small, it's not a specific term, so 13 hours for the iodine 123. But we can still see that's going to be a relatively short amount of time. So these aren't going to be sticking around in the body for years. So the radiation isn't going to be a huge issue. If these were going to be something that was going to stick around for 13 years instead, then we would want to find some other way to kind of go about this process. But since most of them are going to be on the range of hours to days, not going to be anything that's going to be too problematic. And then with some of these, I'm not super familiar with all of these, but I would also assume the ones that are going to be longer half-lives, either whatever they're trying to diagnose is going to already be worse than the radiation, or the radiation itself is just going to be minor depending on which actual isotope it is, because not every isotope is going to be equal in that sense, in terms of kind of how devastating it could be. But with this next piece here, and I'll save this for the next video, is going to start to look at, like I said, the basis of nuclear weapons and nuclear power, and just why those reactions that are utilized are so energetic. And it's going to come down to this equation here, that I'm sure even if you're not familiar with exactly what it represents, I'm sure you're familiar with just the equation itself, just from seeing it in different places. But we'll save that for the next one. That's going to be probably the last video for this nuclear chemistry chapter.